Hello.
Oh, hello.
How are you?
I'm good. Can you hear me okay?
Yeah, I can hear you. Can you hear me?
Okay. Yeah.
Yeah, see. Yeah, okay. That's good. That's good. How are you feeling so far about the midterm tomorrow?
I got kind of scared earlier because I was in lab and everyone was talking about it
Oh,
and
yeah.
and it made me really scared because the they told me Mascal told them the average was 30%.
Oh
So
my God. What the heck?
I
30%?
was like, yeah, like that's like in the past, but I don't know.
That's scary.
I don't know. So now I'm like scared that he's gonna put something like crazy on there.
Yeah, like I can't predict him because this is his first time teaching 118B and like I can't
Yeah.
tell what his first exam is gonna be like until like the actual thing and his practice so far. Like the predicted product was okay, synthesis was
Yeah.
okay, but the vocab one was like rough. Like it
Yeah,
was
no
confusing.
one knows. They're talking about that. No one knows like because he's never taught like vocab, I guess. So
Yeah,
so everyone's like, what? I
yeah.
think you had to read the textbook, but yeah.
Yeah, I know. Yeah. Let's see. Did you have any questions so far?
Um, yeah, I had a question on like the one you made,
Mm.
uh when we're predicting the products B.
Mm-hmm. Let's see. Let's pull
I
that
like
up. Yeah, and after that, let's go over the carbene reactions. Let's see. Okay. Okay. So let's see. B for predicted product here.
yeah.
Uh-huh. Okay. And so if we see these reagents here, what kind of reaction comes to mind?
Um, like you mean like if it's like E1 or E2?
Oh, like what is the name of this set of reagents here? Like the name of the reaction. You see mercury as the first step,
Um,
and then reducing step as the second step.
um, I forgot what it's
Uh-huh.
called.
Yeah, that is going to be oxymercuration, demercuration, right? So if you see a mercury on the first reagent here, then that's going to be oxymercuration, demercuration. And then you could like remember that by remembering mercury, Hg.
Okay.
Uh-huh. And
Yeah.
do you remember if this reaction was Markovnikov or anti-Markovnikov?
Um, I think I think I think it is.
Yeah, it
Is
is
it? Okay.
Markovnikov or anti-Markovnikov. Which one?
It's Markovnikov.
Right, right.
Yeah.
Markovnikov. Right. Which means that it is going to attack on the more or less subside.
The more.
Yeah, which is this carbon right here,
Mm-hmm.
where this ETOH here is the nucleophile. That is not water, right? So when we put ROH there, we are going to attach this group here, right? Where that OET is this OET right there. If let's say we didn't have that and we had water instead, then we would get this, right? But this is
Mm-hmm.
ROH, which our answer is OR.
Okay.
And it attaches to the more subside there. Okay, so oh, okay. So now let's go over the um carbene reactions where a carbene is a carbon with two bonds and one lone pair of electrons. How many electrons does that carbon have in total?
Oh, sorry, I just had a question about the previous one.
Uh-huh.
Do we have to write the other products? Like or yeah,
Uh,
or just that would be the final answer?
yeah, this is the final answer. This is not the answer here because we weren't given water.
Yeah, but would we have to draw out like the mercury plus the ring that you just drew plus what is it, the ester or something like that?
Oh, like the
Like the
mercurium
other
ion, like this right here?
um yeah, like when it breaks
Oh,
and
no,
you
no.
get three things, like like yeah, you get your ring, you get the mercury, and then you get that. I think it's an ester, right? Because it breaks the bond.
Oh, yeah. So this right here is the mechanism. You don't have to draw out these things. Oh, like the other things here, like mercury, liquid, and
Yeah,
then the leaving group acetate here.
yeah. Oh, sorry, acetate. Yeah.
Yeah, yeah. You don't have to include these. The main product is this, which you just have to include that right there.
Okay.
Uh-huh.
Okay. Thank you.
Yeah, no problem. Where now the carbene is yeah. After this, let's go over the peroxy acid and isomerization mechanisms. Um, Carbene is a carbon that is attached to two single bonds and one lone pair right there. This carbon here has 6 electrons, 2, 4, 6, meaning that it is missing 2 electrons. That's why that carbon has an empty p orbital, which makes that carbene an electrophile. That carbene also has a full p orbital that is holding the lone pair of electrons, which makes this carbene a nucleophile. So a carbene is both a nucleophile and electrophile at the same time, right? And there are 3 carbenes reactions you need to know. Like you need to recognize these 3 reagents here. CH2N2 with light or heat or copper. The other one you need to know is um, the Simmons-Smith reagent, which is going to be CHI2 with zinc copper. And the other one you need to know is CHCl3 and strong base KOH. So let's look at the first one here. But let's say we have this alkene right here. And we react that with CH2NH2. So just N2 actually. CH2N2. And let's say under light. This is going to form a cyclopropane, a 3-membered carbon ring. Not an epoxide, a cyclopropane, because this is not an oxygen right there. That's a carbon. So here's the mechanism. CH2N2 looks like this. Right? Where you notice how we have a carbon that's negatively charged and then a nitrogen that's positively charged. When you see this N triple bond N right there, that's the best leaving group we could have. That leaving group is just going to leave by itself and leave as nitrogen gas, N2 gas. And that's going to form our carbene right here. Where, you know how we said our carbene is both a nucleophile and electrophile at the same time? One of the carbons of the alkene is going to attack the empty p orbital of the carbon. At the same time, that lone pair of electrons of the carbene attacks the other side of the alkene, which gives us that product there, where this highlighted carbon is this highlighted carbon right there with its two hydrogens here. It could have been a dash as well. Does that part make sense?
Yes, thank you.
Yeah, no problem. Now let's go over the Simmons-Smith reagent, which is the CH2I2 zinc copper. So the mechanism of this is like this, where we have carbon attached to two hydrogens and two iodine, right? This is going to be an insertion step where the zinc inserts itself between this carbon and iodine, which will give us this carbon, zinc I, and two hydrogens still. And then from here, the zinc I2 is just going to leave, like this zinc I and I is just going to leave and give this carbon a lone pair of electrons, like that, forming our carbene. And then we do the same exact arrows to form our cyclopropane. Where this carbon of the cyclopropane is that carbon right there with its two hydrogens. Does this make sense?
Yes, thank you.
Yeah, no problem. Now let's go over the CHCl3 with strong base example. That will create still a cyclopropane, but this time the carbon that is at the top is going to have two chlorines here. So here's the mechanism. CHCl3 looks like this. That carbon is attached to two Cl's and one H, right? What is the partial charge of that carbon right there that is really that is attached to really electronegative atoms?
Positive?
Yeah, partial positive charge, because all these chlorines here are withdrawing electrons from that carbon. And that makes this hydrogen also really positive as well. And if a hydrogen is really positive, that is really acidic, where the OH minus that we have in the arrow is going to deprotonate that hydrogen and form our almost carbene. But what would be the formal charge of this carbon here with three bonds and a lone pair of electrons?
Neutral?
So you know how carbon is at the fourth column? It wants four electrons to itself. This carbon here has one,
Oh,
two,
negative.
3, 4, 5. Yeah, negative. 4 minus 5, negative. Where we could neutralize this negative charge by just kicking out one of the good leaving groups, chlorine, to form this carbene. But instead of hydrogens now, it has chlorines. Same kind of arrows to give us these products here, where this carbon of the cyclopropane is that carbon right there with its two chlorines.
Thank you.
Yeah, no problem. Yeah, so the most important thing here to know is that a carbene is both a nucleophile and an electrophile at the same time, because it has one empty p orbital and one full p orbital. And it is neutral as well, but it's missing two electrons. Okay, now let's go over the peroxy acid and isomerization mechanism. Okay, so let's first see what this reaction does. When we have let's say an alkene like this, and we put that through a peroxy acid, RCO3H, that is going to form an epoxide like this right here, right on the same side. So that makes this dash, and then the hydrogen here is going to be dash, but we don't have to include that. Right? And then plus minus as well. So when you see RCO3 oxygen like 3 times, that is a big sign of peroxy acid, which looks like this. where this is the peroxide bond right there. When you see a bond between two oxygens, that is a really weak and unstable bond. Right? Now, I'm going to draw the alkene like this with its R group. Let's say that methyl and oh no, this has to be trans. So that. Okay. And then I'm gonna redraw this oxygen here, this peroxide as this right here. Let's say HO. Okay, so this peroxide bond, peroxy acid, is this exact peroxide acid here. This alkene is that exact alkene right there. Okay. The oxygen with the hydrogen is gonna end up as the epoxide oxygen, right? Where this oxygen here is a electrophile. It looks weird because usually oxygens are nucleophiles because it has the lone pair of electrons that it's going to attack an electrophile. But in this case, this is an electrophile because this right here is a good leaving group. This is a good leaving group because when it leaves as a stable negative charge on that oxygen right there. Do you know why this negative charge is stable as it leaves?
Because resonance.
Great, because of resonance. That could do resonance with the carbonyl right there. So this alkene carbon here is going to attack that electrophilic oxygen and then kick out the leaving group to make a double bond between that carbon and oxygen. And that's going to be a problem because we're going to break the octet rule here. That carbon is going to have 5 bonds where we're going to pop up the double bond onto this oxygen right here, which gives that oxygen a negative charge, which that negative charge is going to grab that hydrogen right there. Right. When that happens, this bond between oxygen and hydrogen is going to give that oxygen a negative charge, where that negative charge oxygen is going to attack the other side of the alkene at the same time, which gives us our epoxide here, where that yellow highlighted oxygen is this one. And now we also have this oxygen, OH, R. Let's say this blue highlighted oxygen is this blue highlighted oxygen, which made a double bond between that oxygen and carbon. And this pink oxygen there is this pink oxygen here, which grabbed this, let's say, green hydrogen, which is this green hydrogen right here, right? So we also form carboxylic acid as a side product.
And then also, I don't know if you didn't, or is it like implied when you're drawing like the O grabbing the H that the pi bonds are going onto the oxygen and then it's going to grab the H?
Yeah, it's implied like that, where the
Okay.
double bond is going to go to the oxygen first, which gives it a negative charge, which attacks the H right away.
Okay.
This all happens in one step.
Got it. Okay, cool.
Yeah. Now let's go over isomerization, which is going to be more intuitive than that peroxy acid mechanism, where in isomerization reactions, we are converting a less stable double bond to a more stable double bond. So there are different stability factors for double bonds. One is hyperconjugation or substitution. The more substituted the double bond is, the more stable it is because of more hyperconjugation. Substitution. The other one is going to be E and Z, where E alkenes are more stable than Z alkenes because of less steric hindrance. Okay. The other one is going to be about ring strain. Right. where ring strain increases from right to left. That means stability increases from left to right, and then energy increases from right to left. Right. So now let's do isomerization, where the reagent for that is H2SO4 and heat. So let's say we have this double bond right here, and we put that through H2SO4 and heat. Since we have a strong acid, we have to look for our most basic atom, which is going to be one of the carbons of the alkene here. We want to form the more stable carbocation, which is this more substituted side right here. That means that the less substituted carbon of the alkene is going to get protonated by the strong acid. That's the carbon that grabs the hydrogen, which means that this more substituted carbon lost the bond, forming a carbocation here. Whenever we form a carbocation, we always look out for a rearrangement step, like a hydride or methyl shift. In this case, we could do a hydride shift to convert this secondary carbocation to the more stable tertiary carbocation here. Then we have to consider all the beta hydrogens and look for the most substituted beta hydrogen, which is going to be this one here. So we could use the conjugate base to grab that most substituted beta hydrogen to form the most substituted double bond, which forms this tri-substituted double bond now. 1, 2, 3. So we converted a less stable mono-substituted double bond to a more stable tri-substituted double bond.
And is it just based off of the like carbon being primary, secondary, tertiary?
Yeah, that's right, that's right.
Okay.
And another isomerization is that it could still be di-substituted, but it could be cis, and we could convert that to trans alkene, but they're still di-substituted, but this trans is more stable, where the mechanism is going to be the exact same thing, but there's a slight change here because there's no carbocation shifts, but there will be a sigma bond rotation here, which will rotate it into the trans-like structure. And then we do the E1-like mechanism to form the more stable trans double bond here.
Okay. And I doubt he give it as a mechanism, but like for the bond rotation step, would you just draw the like the rotational arrow showing that you're going like you're rotating about the bond to make it, or like the one, yeah, that one.
Oh yeah. That's what I like to do to show like what's going on, but it's optional.
Okay.
Yeah. You could just draw this curly arrow to show that this is the redrawn version of it, and then just draw the trans-like version.
Okay.
Yeah, I just drew that rotating arrow to show what's actually going on. A tricky type of isomerization question that might show up is ring expansion. So say we have this right here, and we put that through H2SO4 and water. We are going to protonate the less substituted carbon to give us our most stable carbocation in the Markovnikov position. And then here, it seems like we don't want to move this carbocation because it's already at its most stable position, but we do want to move the carbocation here to be able to do something called a ring expansion. And I'll show you that right now, where we could do that by doing a hydride shift, which moves this whole hydrogen with its 2 electrons there. This carbon loses a bond, which gains a positive charge. And if you see a carbocation one away from an unstable ring, it's going to expand to the more stable ring by expanding to one extra carbon. So let's say that this is going to be carbon 1, 2, 3, 4, and that carbocation right there is going to be the added carbon, carbon 5. So this is the weird migration step here, where the bond between 1 and 4 is going to migrate and make a bond between 1 and 5. So let's draw that. We know that we're going to make a 5-membered ring. Let's just draw that template out, which is that. Now let's do 1, 2, 3, 4, 5. This is the new bond that was formed right there, the pink circled bond. There was no bond between 4 and 5, but we migrated that bond to 4 and 5 right there. Right, where at carbon 1, we see that there was nothing, but at carbon 5, there's 2 methyl groups. So let's just put those 2 methyl groups there at carbon 5, because there are 2 methyl groups at carbon 5 there. Carbon 1 right here used to have 4 bonds. 1, 2, 3, 4. But now carbon 1 has 3 bonds. 1, 2, 3. Because it lost this pink circled bond after the migration step, giving that carbon there a positive charge because it lost the bond, right? And then whenever we form a carbocation intermediate, we always look out for a shift, like a hydride shift or methyl shift. In this case, we could do a hydride shift by moving this, a methyl shift, by moving that methyl group onto that carbocation, which that blue methyl group is there. We have a carbocation here. And then we finish up the reaction by doing the E1-like mechanism, deprotonate that most substituted beta hydrogen, make the most stable double bond here. So this was ring expansion, where we made a less stable double bond to a more stable double bond with less ring strain. So the weird step here was probably this migration step. Okay. So let's see.
This is about a different reaction, but for carbenes, I was like a bit confused on like knowing when it's like wedged or dashed or just planar, because like the majority of the time, isn't it just gonna be achiral because there's gonna be like 2 hydrogens coming off of the carbons, so like none of those are chiral centers.
So these right here would be planar because that's not a chiral center right here.
Mhm.
But these right here are
Oh,
chiral
okay,
centers.
those are chiral.
Right, which was why we include stereochemistry for those carbons, but no stereochemistry for the top carbon with the 2 hydrogens.
Okay, I see. Is that like typically the case with the carbene?
Yeah, that's typically the case, but I've also seen some examples where they just like put bonds like that,
Okay.
with no wedge or dash. They just made it flat like that as
Okay.
well.
Oh, and then I don't know how to send it to you. I'll just show it to you. I'll just send it to your Instagram because
Oh yeah,
it's from
let me
this
get.
is from the textbook. I was
Uh-huh.
just curious if that was correct, but then also if those were diastereomers, because there was like some pre-existing
Yeah.
stereo.
Let me see. Oh, I see. Okay. So, that should be correct because it's anti-Markovnikov, and since the methyl group is so small, there's no like major product. Like those 2 should be equally major.
Mhm.
Yeah.
Okay, and then would they be diastereomers?
Yeah. Wait. Let's see. Yeah, there would be diastereomers.
Okay, because the pre-existing stereochemistry.
Yeah, that's right. That's right.
Okay.
Uh-huh.
And then even if it was like even if you were given like a pre-existing stereocenter, but it was planar, it would still be diastereomers, right? Just because you could count for
Mhm.
groups.
Yeah,
It's
yeah, yeah.
kind
If
of
it's a pre-existing chiral
RS.
center and it's planar, it's still diastereomers.
Okay.
Right. Where that methyl group that is wedged at the top stays untouched, so nothing happens to that. But when we do hydrogen oxidation, the alcohol could be a wedge or a dash, where we see that this chiral center changes, but this chiral center here stays the same, making these diastereomers. And they're both equally major because even though this methyl group is going up, it's not a really big group, so the alcohol is still able to attach on the top
Yeah.
side there.
It would only be like terbutyl if then.
Uh-huh.
Okay.
Right, terbutyl or phenyl group,
Okay. Yeah.
like benzene, like that.
Okay.
Let's see. Okay, let's try these three predicted product problems here. So we have an alkene with HBr, and this here looks really weird, but think of that phenyl group as an R group. So this is going to be ROOR. When you see ROR with HBr, that is going to be an anti-Markovnikov reaction, where the bromine will attach to the left subside of the alkene, giving us bromine here. And this reaction here only works with HBr, RSH, H2S. Yeah. So ethyl or HBr only. If you have HCl, then ROR would not do anything. Would just be ignored, right? There still will be a reaction where we want to protonate the less subcarbon to form the more stable carbocation. And then whenever we have that carbocation, we always look out for a rearrangement step, like a hydride shift or a methyl shift. So we could do a hydride shift to make the more stable tertiary carbocation here. And then the CO minus can just come in and attack, giving us our final product here. Where the ROR in this case does nothing because HCl is not going to react with ROR. The only things that react with ROR are HBr and thiol, sulfur. Right? Just like this thiol here. This is the RSH, which will do anti-Markovnikov and add the sulfur group at that less stable position there, where ET is ethyl, 2 carbons. Right? Okay. Yeah,
Hey Brian, I have a question.
yeah.
It's over oxymercuration, demercuration.
Mhm.
For all the products that you're gonna get after oxymercuration, demercuration reaction, are they all gonna be planar, or will they have a stereocenter?
Yeah, so it depends on what the molecule is. So it will be planar if there is no chiral center. So if we have that kind of alkene and we put that through oxymercuration, demercuration, then we know that we are adding alcohol on the more subside, which is this one right here. since this carbon is not a chiral center because it has two methyl groups, then we don't have to put wedges or dashes. But if we have something like this, where we do the same exact reagents for oxymercuration, demercuration, right, then we have to put stereochemistry because now this is a chiral center with four different
Oh,
groups:
alright.
an ethyl, alcohol, methyl. Oh wait, actually no, that is not a chiral center.
Yeah,
Let
there's
me,
a similar.
there we go, there we go. Yeah, in that case that I just gave you earlier here, you don't, everything's gonna be planar in that case.
All right. Yeah, because I was looking like at Leibniz's practice. There were every single one doesn't have a stereo center, even though like all of them have stereo centers, but they're still in planar. So that's why I was wondering.
Oh yeah, that's a Leibniz thing. Like she just assumes because we know that if we have a chiral center here, right, we could have wedge or dash, but this could have been the enantiomer version as well, where we do plus minus, where this alcohol could have been a dash and this isopropyl could have been a wedge. If that's the case, right, like let's say the other product is this dash OH and the isopropyl is a wedged isopropyl, that those two things are the exact same as that right there, right? Where
Oh,
this
alright.
bond could have been a wedge or dash, and that bond could have been a wedge or dash as well. But they're forced to be anti to each other. Like therefore, if one is wedge, the other one has to be dash.
All right. So there's no stereo specificity, right?
Yeah, no specificity here.
All right.
Uh-huh.
All right. Thank you.
Yeah, no problem. Because the OH could be either dash or wedge. Or isopropyl could have been a dash or wedge. Mhm. Okay. Let's see. Any other questions? Or which part of the extra practice exam did you guys want to go over? Let's see. Okay, let's try this E2 reaction here. We have a strong base, CH3O minus, that is unhindered, right? And we have a good leaving group here, bromine. We know that this is going to be an E2 reaction that's going to go for the Zaitsev product. So we have to draw out all the beta hydrogens. This is one beta hydrogen. And these are the two beta hydrogens here, right? For E2, we want to look for the anti-paraplanar transition state. And that means that we want to look for the beta hydrogen that is anti to the leaving group. Since this leaving group is a dash, we want to look for the beta hydrogen that is a wedge, right? And also we want to make the more stable double bond as well because we have a small strong base here. So that means that we want to grab this hydrogen because it's the most substituted one, which will give us the more stable double bond, the most substituted double bond. But we cannot do that in this form because this hydrogen here is not anti to that leaving group. So what we have to do is that we have to rotate the single bond and rotate these three groups here, the isopropyl, the methyl, and the hydrogen. We want the hydrogen to be dash, so we're going to move that hydrogen there. That forces that isopropyl to become planar, and then that planar methyl becomes a dash. So rotating everything, we are going to get dash methyl, wedge hydrogen, and a flat isopropyl there. Now, after we rotated everything, now we see this beta hydrogen is anti to that leaving group, where this O minus can grab that hydrogen, form a double bond there, kick out that leaving group, which gives us this alkene right here. There is a shortcut for this, right? Like let's say we do it wrong first by grabbing this H right away. That is not anti-periplanar to that leaving group. If we do that, we are going to get this wrong product here. Right. This is the wrong product because this hydrogen here was not anti to that. To get to the right product, we just swap these two OR groups here. Right? And when we swap it, we would get our correct answer here. So that's a shortcut way. Right. This can only happen if we are in a linear chain that is able to do rotation. Let's say we are not in a linear chain and we had a ring right here. We have a small strong base, ethoxide, and this is our good leaving group right here. This is a beta hydrogen. These are also beta hydrogens. Since this is a small strong base, we want to look for the more substituted beta hydrogen, which is this one right here, which is going to form the most stable double bond. But this is not anti to this leaving group because they're both dashes. So we can't attack that hydrogen, form a double bond there and kick it out. And we can't do the shortcut as well because this bond here can't rotate since it's in a ring. And if it's in a ring, then this is locked in into that place. We can't make that anti, which means that this base is forced to go to the left subside by grabbing this other beta hydrogen here that is anti to the leaving group, which will form this product here, the less stable double bond, because that's the only place where it could go, where that methyl stays as a wedge because nothing touches that carbon here. So that was the E2 reaction. Let's see. Yeah, that's also E2. Okay. Let's try this one here. This IPROH is isopropanol, where isopropanol looks like this right here. We have an alcohol with this OR group there. H2SO4 is a strong acid, which is going to protonate this alkene right here. We want the more substituted carbon to have the carbocation. So that means the less substituted side has to get protonated by the strong acid. When that happens, we form the carbocation on the more subside here. And whenever we form a carbocation, we always have to stop and look out for any rearrangement step, like a hydride shift or methyl shift. In this case, we could do a hydride shift. Because this is a secondary carbocation here, it could move here to become a tertiary carbocation, which is more stable. So this hydrogen here can move there, which will give us this tertiary carbocation here that is more stable, right? And then from here, once we have that more stable carbocation, the alcohol can attack that carbon right there with the positive charge. Once that happens, we have this new bond right there between the oxygen that attacked that carbon. And that oxygen there, we know it's attached to this R group and one H still. This oxygen with 3 bonds will have a positive charge. The very last step here is to neutralize this positive charge by deprotonating it, which will give it a lone pair of electrons, and it is now neutral. Final answer.
Does that only happen with IPR?
Oh, yeah, it doesn't always have to be IPROH. It could be any ROH. It could be ethanol, which is ETOH. It could be propanol. It could be sec-butanol, any ROH, right? Where the answer is always O and whatever the R group is in the alcohol. Like the R group here could be any random chain.
Okay. It just needs to be H2SO4 and an ROH group.
Yeah, an
Okay.
ROH group. If you have water instead, right, like H2O, then your
Yeah.
answer would be OH.
Okay. Okay.
But the same exact mechanism happens. Like the water would attack, and then we would get O, H, H with the positive charge. Where the last step is just to deprotonate and take away one of the H's, but we still have an OH here.
Got it.
Uh-huh. Okay. Have you guys tried the other problems here yet?
Not yet.
I see, I see.
Yeah.
Do you have any like reactions that you're unfamiliar with that we could go over, or we could like just do random problems here?
Um, we could do random ones. I
Mhm.
don't think I got like every single reaction.
I see, I see. Uh, do you recognize this one here, this reagent, the CH2I2 with the zinc copper?
Not very much.
Uh-huh. So let's go over that before we do
Okay.
that reaction. So when you see any of these three things, right? Like let's say we have an alkene like this. If you see CH2N2 with light or heat or copper, you're going to form a cyclopropane, a three-membered carbon ring. Like that. You could also see CH2I2 with zinc copper, which is also going to give you a cyclopropane, a three-membered carbon ring. If you see CHX3 under a strong base like KOH or NaOH, then you are going to get the cyclopropane where the very top carbon has two X groups, where X can be chlorine, bromine, or iodine, right? So these are the three carbene reactions, right? So in that case, what do you predict the product to be here, given this reagent with this alkene?
Can I go back? Can you go back really
Yeah,
quick?
yeah.
So is it just the enantiomer? I know, like, yeah, the triangular.
Yeah, the triangle cyclopropane,
Oh
where
well,
they have to be on the same side, so they could be wedges, right? And if they are wedges, what does that make this isopropyl group bond there?
dashed.
Yeah. Or it could have been this as well. And that's it.
And these are enantiomers, right?
Yeah, these are enantiomers.
Okay.
But if we had this, what would these be now?
Diastereomers.
Yeah, diastereomers. If there is already another chiral center existing, then they are diastereomers because we see that this chiral center and this chiral center changed, but this chiral center stay the same.
Okay.
But we didn't have that before, so those were enantiomers before.
Okay.
Okay. So now let's try this reaction here. When you see D2 or T2, think of it as H2. The reason why they might give you D2 or T2 is because they want you to draw out the D or T out explicitly. Because if they give you H2, you could just say that that H is invisible. Right, so this is hydrogenation reaction, which means that we're going to add hydrogens or D or T on these carbons here. And we know that in hydrogenation, is it syn addition or anti-addition?
Sin.
Yeah, syn addition, where it could either attack on the top side, the wedge side, or the bottom side, the dash side. Which side do you think is more stable? Which one can attack better, easier?
Dash. Like
Right,
yeah.
dash. That's because the top side is already so bulky, too much steric hindrance there. It's hard for the Ds to get to there. So there's gonna be a dash D here, a dash D there. That's the final answer. Major products. Right? Because if your professor give you H2 PDC, then you could just say this is your answer right here, where the H's are invisible, right? But since professors want to test you on the stereoselectivity, like they want you to know, test you if you don't, if this is syn or anti, they will use D2 or T2 to show, to test if you know that these are going to be on the same side, like that.
Yeah.
And also, and which side is more stable as well, the top or bottom side, depending on what's around it.
If it was wedge, it would be like a minor product.
Yeah,
Or
if it
is
was
it not
wedge,
possible?
yeah, that's right. It is still possible, but it would be minor. But
Okay.
it will still be possible.
Okay.
Mhm. But that's a minor product. And that could be a vocab question too as well. Like why is this the minor or major products
Okay.
like there? This is minor. Right. Okay. Let's see. Let's try this mechanism problem here. What do you think is gonna happen in the first step?
Does HCl gets the H in it?
Uh-huh. So which carbon would grab the H?
The more supp one.
Yeah, so the more sub one, we want the carbocation there. If the more sub one grabbed
Okay.
the H, then we would get the carbocation on the less sub carbon,
Okay.
because the more sub carbon still has 4 bonds. That means the less sub carbon is going to attack the H to form the carbocation at the more sub carbon right here. From here, what do we have to do?
Um, rearrangement.
Rearrangement, right. And what kind of shift do we want to do? Do we want to do a hydrate shift or metal shift? Can we even do a hydrate shift here?
No, it's
No.
oh,
Right. So methyl shift, that's right. To form the more stable tertiary carbocation there. Right. And then what happens next? How can we go from here to here?
the Cl minus will just go to
Attach.
the yeah.
Right. That's it.
Just quick question. Is
Uh-huh.
like a primary carbocation possible?
It is only possible if it is allylic. So
Oh, okay.
this is possible. This is not possible.
Oh, okay.
Right. Because this is way more stable than this one, because this can do resonance. Mhm. Okay, so now let's try. Okay, let's try this nomenclature problem here. How do we want to number this structure?
From left to right.
Yeah, that's right. Because we have an alcohol versus an alkene, and we know that an alcohol has higher priority than an alkene. So we want to number this 1, 2, 3, 4, 5, 6. Wait, And these are our substituents here. Since our base name is 6 carbons long, we have hex. And then since alcohol is our base name, we want the last suffix to be ol. But we see that there's an alkene at carbon 4, so we have to say hex 4 ene. And then the alcohol is at carbon 2, so that's 2-ol. This is the very end of the name right there, which is the parent chain.
Hmm.
Our substituents are, we have a chloro on carbon 1, we have an ethyl on carbon 3, and we have a methyl on carbon 4. And we also have stereochemistry here. Is this an E or Z isomer?
E.
Yeah, E, because the highest priority groups are on the opposite side. Right? So putting everything together, we have E, and we have to put alphabetical order now. We know that C comes first, so it's 1-chloro, and then E comes after, 3-ethyl, and then M comes after, which is 4-methyl, and then the parent chain, hex, 4, ene, 2-ol. Like that. Okay.
Yeah.
Okay. Try this nomenclature problem here.
Is it three propanil?
Uh-huh.
Oh, well, wait.
So where's our number 1 carbon at?
At the OH.
Right here, right. And then do we want
Yeah.
to go counterclockwise or clockwise? So if we go counterclockwise, you know how our second substituent is carbon 3?
Yeah.
And if we go clockwise, our second substituent is also carbon 3.
Yeah.
If there's a tie, then we choose the one that has the first alphabet.
Yeah. Okay. So counterclockwise.
Right, counterclockwise. So this is going to be 2, 3, 4, 5. So 3 bromo, 4, and you know how the substituent here, we have an alkene that is outside of the main chain?
Mm-hmm.
This alkene here is 3 carbons long, which is going to be propenol. We use enol to show that it's outside of the main chain.
Mm-hmm.
But the double bond starts at carbon 2. So we have to put parentheses to show that this is a complex substituent. 2-propenol. And then cyclopentanol.
Okay.
The propenol shows 3 carbons long. The 2 shows where the alkene starts, which is at carbon 2 of the propenol. Cyclopentanol. If it was, let's say, 3 bromo, 4, 1 propenol, cyclopentanol, then this would be our structure here, where you notice how the alkene now starts at carbon 1 of the propenol.
Yeah.
Yeah, so it also depends on like what your substituent is. This is your substituent where the double bond starts at carbon 2. Here, the substituent, the alkene starts at carbon 1, which is why it's 1-propenol, and then the suffix there. If you had ethanol, then you don't have to put any numbers because let's say this is a substituent, ethanol, there's only one carbon where the alkene can go, which is carbon 1, because it's only 2 carbons long. So you don't have to put 1 or 2 ethanol. You could just say ethanol, and then it's assumed that it's right there.
Okay.
Yeah, that is it. Any other questions?
So like, yeah, just in C, it will be acinidine.
Ethylidene, right.
Okay.
Ethylidene, at carbon 4, because this is 1, 2, 3, 4, 5, 6, 4, ethylidene, cyclohexanol, where the ylidine part shows that half of the substituent double bond is on the main chain and the other half is not on the main chain.
Okay.
Right. You got it.
Yeah.
Uh-huh.
Thank you so much.
Yeah, no problem. Good luck tomorrow.
Thank you. Good.
Mhm.
Have a good night.
You too. Bye.
Bye.